Good morning. A warm welcome from my side. My name is Andreas Lock. I joined the ENAMS team in 2019, late 2019, and since then I'm working together with Klaus Eichel and the rest of the team. My focus or my work area is more the software part. So I appreciate very much that I can introduce ENAMS to this auditory, and I will talk about, say, the results and outlook after 5 years of operation of ENAMS. So this is the agenda. I shortly will touch the motivation. So ITU is dealing with radio noise since a long time. So I show some results for different ITU locations, but also for different kind of interferers. And we see also some nice effects also with ENAMS, like Mögel-Dellinger. So I will touch the IAU request. That was the start of the ENAMS 2 project because we had no receivers more available. And I shortly will give what we plan to do in the Outlook section. And finally, a short summary. Yeah, ATU is dealing with radio noise for many years. So for the efficient spectrum management and the design of radio links, the minimal man-made noise is of significant importance. So up to now, spectrum management and also design of radio links is based on the well-known curve of the ITU P372. The measurements, which are shown here in the middle of the slide, were done in the 1960s of the last century, and they are the foundation for many design considerations. But due to the unbroken proliferation of electronic devices and the advent of high power supplies for the, let me say, substitution of fossil energies with electrical energies, the noise levels, radio noise levels might have changed. Therefore, the knowledge about the development of the interference levels seems to be a must for us, because then we can talk to the authorities and bring this into the awareness and discussion. So what is ENAMS? ENAMS is an interference field strength measurement system. That's an automatic reception system distributed mainly throughout Germany for recording of the interference level in the frequency range between 66 kilohertz and 31 megahertz. So, and the ENAMS project was decided by end of 2017. It was initiated by the DRC-EW, because the Bundesnetzagentur, the German Federal Network Agency, did no longer publish general interference measurements after 2011. We do not know if they are still measuring and monitoring, but they were not published, and therefore the increase in the general interference levels in the last years is not documented and not communicated. So, and now with ENAMS, amateur radio is in a position to measure the relevant interference levels itself and can contribute to the discussions, because we found out that in some cases improper measurement systems and procedures were used leading to incorrect results. And therefore, it's in interest of amateur radio that we can present correct measurements and the correct knowledge about the interference solutions, and can discuss it further. So, a short technical summary for ENAMS 1.0, the first generation of the ENAMS receivers. So it's a direct conversion, SDR with zero intermediate frequency based on the red pitaya. So it has an active antenna covering the frequency range from 66 kilohertz to 31 megahertz, and the sensitivity of this antenna is always below the ITU standard rule by several dB. So the front end, RF front end, has two active channels with gains of band amplifiers, which are adapted to the noise levels, compromising between sensitivity and large signal dynamics. Because in the lower frequency, we have strong medium wave and long wave transmitters with large signals. Therefore, it's more the signal dynamics. At the higher frequencies, it's more about sensitivity. Therefore, we use different gains in the two bands. All stations, and I think this is important, all stations are calibrated individually. So Klaus does, let me say, a calibration measurement with a special device before devices, the receivers are shipped. So data storage and processing is done via a central ENAMS server, and the results are shown on the ENAMS homepage, which can be reached under www.enams.de. So therefore we show the diagrams of the previous and the last or previous 10 days, heat maps, spectra, and other diagrams. So currently nearly 70 stations are deployed in Germany and internationally. And I think ENAMS has proven in the last years to be a practice-oriented tool for the monitoring of electromagnetic interference. So this is a block diagram of the ENAMS-1 SDR receiver. On the left-hand side, the active antenna is shown with a cable. So the cable used some ferrites on to block disturbances or interferences which come from the power supply and from the house. So if we look now into the diagram, you see the power supply on the top. Unfortunately, it's written in German. So to provide the, let me say, the energy for the active antenna, then the signal goes over a low-pass filter, which a cutoff frequency of 32 megahertz, and reaches a diplexer. So we have a low frequency parts, the Tiefpass, which has a cutoff frequency of about 7.5 to 8 megahertz, and subsequent gain amplifier with 10 dB amplification or 10 dB gain. And in the lower part, we see the high pass, also with a cutoff frequency of 7.5 megahertz to 8 megahertz, and a gain amplifier or band amplifier with a gain of 20 dB. So the outputs of the gain amplifiers go to the inputs, the two inputs of the red pitaya, and are processed. So this is a overview over the whole ENAMS system, the system diagram. So on the left-hand side, you see one receiver. Currently here are shown 50 in Germany, but we have now 69 to be exact. And the main part of the ENAMS server is, let me say, SQL database. So the server is an i7 computer with about 32 gigabyte of main memory, and has a disk system, a RAID system with effectively 12 terabyte of disk space. So because it's a RAID system, 8 terabyte can be used for data storage. And you see in the diagram, in the SQL database, we have different tables where the different information go into. So we also use a backup server. It's in a different location, physically different location. So we have a backup so that we do not lose data during our operation. So in case of a failure of the main server, we can switch over also to the backup server to take over, let me say, the operation and data transfer to our web page. So on the right-hand side, you see the part for the analysis, the data analysis, and the web server. And on the right-hand side, the diagrams are examples which you can see on our web page. So now I come to the results. So, the first ITU location is a rural station, quite rural we do not measure because quite rule from the definition, there is no radio amateur, no human beings. So we have some stations placed at rural stations. One, and this is the quietest station, is Landshut, number 15. And you see on the right-hand side a line diagram. So this is a calculated noise floor from the spectra we take over. And as you can see, if you look to the frequency range of about 10, 15 megahertz, the signal, the noise floor is well below rural. This is the quietest station. So we do about 144 measurements per day. And when we have collected all the data from one day, we are able to draw a heat map. This you can see on the left-hand side, because the heat map is a very compact and comprehensive information about the noise situation of the previous day. And what you can see here are the dark area. If you look to the color bar on the right-hand side, so this dark blue color corresponds to -5 dB compared to the rural level. As you remember, the lines in the ITU diagram were slanted, but for better resolution and to make reading the diagrams easier, we have rotated the lines by 45 degrees, and we show all noise floor levels and amplitudes relative to the ITU rural level. That makes it easier to read the diagrams. So in this dark blue color corresponds to a level which is below ITU rural. But what you also can see, you see this light blue area on the upper left and also on the upper right, and you see it also in the middle at lower frequencies. So in this blue area is due to the damping of the D layer during the day, because the light blue signals are interference signals which come from a larger distance. So it comes over to the receiver through the sky wave. And we guess that this noise comes from cities like Munich and other big cities, which are transferred to the receiver. So, and during the day, the signal is blocked due to the damping of or attenuation of the D layer. And what you also can see is the rise of this light blue area then is due to the maximum usable frequency, because this frequency goes up through the day and falls in the late afternoon, evening. And this explains why you can see the dark blue areas early in the morning and late in the night. You see also some, say, bricks or these nice pixels, which come from distant thunderstorms. So Michael Hartje has shown in a conference, amateur radio conference 2 years ago, that these pixels come from thunderstorms. We waited for a day where we had no, let me say, bad weather conditions in whole Europe. There were only some thunderstorms in the Mediterranean area, and therefore we are sure that these pixels come from the from thunderstorms. And the technical reason is we measure 1 second for each 1 megahertz segment, and if the signal is very, very high in this 1 second, it gets this light blue or green or yellow color. So if we proceed now to the residential next location type, that's a residential location type, and we have here the residential station in Weißenhorn. That's close to Klaus's QTH. So what we see here, so the diagram has a more, let's say, yellow and greenish color. But what you also can see are these dark blue horizontal stripes. And these stripes are typical located at the amateur frequency bands. And this is shown very clearly on the right-hand side. So on the right-hand side, you can see that the average noise floor is on residential level, but at the amateur radio bands, we have these notches which go even down to rural level in some frequencies here. And in the morning time and in the evening, you see at about between 10 and 15 megahertz green or yellow areas. These are some disturbances, but the source is not known to us, which is disturbing here. So this is a typical diagram for a residential station. And now if we proceed to the city station, you can see on the right-hand side, the average noise floor level is on city level or even above. The heat map shows, therefore, more yellow or greenish color. And during today, you see at about 8 to 9 megahertz green to yellow bar, which comes from operation of, let me say, industrial companies or other interferers in that area. So, but there are also other cities which show a better situation, and this is the station in Munich, number 49. If you look to the line diagram on the right-hand side, you see that in the morning, at lower frequencies, and during the day, the average noise level is about city level, but what you can also see that we have the notches still in the city, and the bottom of the notches reaches down to the residential level or even below. But during the day, if you look to the time here, these notches are filled up with noise by unregulated noise sources. And you can also see it in the heat map. During the day, we have a lot of disturbances and interferences, which is seen by the which is seen here by the greenish or yellow color in the heat maps. So now we come to different kinds of interferers, and the first example, what I want to show is interferences caused by VDSL. And if you look to the heat map, you can see these yellow lines at about 3.5 to 5 megahertz and 8 to 12 megahertz. And they also clearly show up in the line diagram here between 3.5 and 8 to 12 megahertz. And these disturbances are associated with VDSL. Because if the installation of VDSL is not properly done, then you have emittance in the uplink sections of the VDSL spectrum, because your router is sending a signal to the counter station, and if there is no good shielding and screening of your telephone line, then you can see these signals, which is done here. And also there are no other notches visible in this diagram because these are completely filled up with interferences, with noise of interferers here in all the frequencies. There's another interferer, which now really is nasty, that is PV installation. You can see it because you have the disturbances only during the day, and it covers nearly all the frequency bands. In this diagram, you see it at lower frequencies and higher frequencies because the noise signal is sent out from the DC lines, and therefore with each installation, so they have a different length with the DC lines, and they have different, let me say, transmitting properties. For certain lengths they are in resonance, for other lengths the signals cancel out, and therefore the diagrams have always a different shape depending on the PV installation. But you see the disturbance level is more in the orange and red part, so the disturbance levels are very, very high. So in another, let me say, kind of interferer are the so-called optimizer. So some of the PV installations use optimizer. These are small impedance converters. So if you have shading on your panels, the optimizer transforms the impedance so that you have maximum current through the whole set of panels. So, and these optimizers communicate with the inverter via PLC on the DC lines, and you can see the signal quite clearly here. So every 200, or here in the spectrum, every 200 megahertz, you see this peak here, and it only exists during the day. In the evening, the signal is gone. So now we see also other optimizers which have, let me say, frequency delta of 100 kilohertz, and yeah, this is a very disturbing and annoying situation. So another interferer are LEDs. So this is close to Weißenhorn, or in the city of Weißenhorn. They test different LED street lamps, and what you can see here is a light blue area in the morning, but also in the evening. These are the times when the street lamp is operating and the power supplies are causing some noise signals, which can be seen in this diagram here. So I promised at the beginning that with ENAMS we are also able to see different effects, and one I want to mention here, because it's very nicely seen, is the so-called Mögel-Dellinger effect. So on 10th of May of last year, we had strong solar activities, and at 8 o'clock, a little bit later, and 2 o'clock UTC, we had a complete shortwave dropout, which can be seen here, because the propagation, was gone due to strong solar flares. And the first drop was also preceded by a strong radio burst. And because in the Landshut station we have it's a very quiet station, so this effect could be very clearly seen. And we had a double check with one station in the United States, in Virginia Beach, and at the same times, let's say these dark lines show up, and we were sure that this is a really global effect. And for confirmation, we looked also into the New Zealand station we have, and this effect was not seen because New Zealand was at that time, let me say, on the backside of the Earth and not seen by the sun. So IAU, there was an IAU meeting by end of 2023, and the ENAMS team, Klaus Eichel, was awarded for the successful contribution for the amateur radio interference monitoring. And because some of the countries in the IAU Region 1, or most of the countries in the IAU Region 1 have no monitoring. Besides South Africa, you have your own system. And those who use ENAMS 1 systems, about 16 receivers are distributed. And therefore the IAU encouraged the DRC to provide more ENAMS units to enable the member societies to do their own interference monitoring. That was the start and the birth of the ENAMS 2 project, because we had no more ENAMS 1 receiver available. And then IAU member societies have the possibilities to do their own measurements and approach the responsible authorities for frequency management with their locally acquired data. And if the IAU, I think they are planning joint activities in many countries, this will help to form an alliance for the protection of amateur radio frequencies and beyond, because we see outside the amateur radio bands, let me say, noise levels have increased much more than in the amateur radio bands. So what did we learn from ENAMS 1 when we started to think about ENAMS 2? The mechanical stability of the radiator was too low because we have some of the radiators broken to changing wind loads. And what we also see with the red pitaya, the red pitaya is a very, very nice device, but the local memory is too limited because we can save only 1 day of data. Otherwise, the memory is filled up if the internet connection is broken, it's not available. And also the computational power of the red pitaya is too low for further developments. So we have quite a number of ideas how to develop the system, ENAMS system further, but this cannot be done with the red pitaya. So also with ENAMS 2, we will include the frequency response of the antenna system in the alignment procedure. So Jörg Logemann, the designer of the antenna, has given us all the data. I will touch it later. So we can also compensate for the variance in the K factor of the antenna. So now with ENAMS 2, we have a local storage and the measurement data can be stored locally and the RX operates without internet connection and also can be operated without access to the server because they have the calibrated measurement data also available on the station. And also we will have the IQ data for about 1 hour for people who want to do their own evaluations and their own experiments with the IQ data. They are made available for 1 hour because with each run, every 10 minutes, we generate 310 megabyte of IQ data and we hold it in the memory of the computer and therefore only 6 measurements at 1 hour is available. And the mechanical stability of the antenna is improved. So this is the, let me say, characteristic now of ENAMS 2. We have more computing power, which shortens the time of the FFT because we have added a Raspberry Pi 5. So I also touched it. We have the improvement of the transfer function by additional adjustment of the frequency response of the antenna. We have the local storage of IQ, raw, and calibrated data. And the system can be operated without access to the server and without internet connection. The mechanical stability of the system has been very much improved. You can see it here on the right-hand side. So it's a very stable setup now. And it's, improved for use in harsh environments. And the receiver system is also fit for industrial production by an EMS, electrical manufacturing service. The first generation was handmade by the team, but we cannot do it longer because I think we spent more than 4,000 working hours and we could do that only once. And what we also plan is assessment, third-party assessment to get independent proof of our measurement capabilities of the antenna as well of the receiver, and we want to get a quality label. So this diagram shows the signal path only, it's a block diagram. So we have the active antenna, we have the low pass filter, we have the different passes, the low pass and the low band and the high band with the different gains of the band amplifiers. The red pitaya provides 2 independent SDR receivers, which are shown here, the AD converter, the digital mixing, and then 2 low-pass filters. The ARM cores in the red pitaya are no longer used intensively, and we get the IQ data here, feed it to the Raspberry Pi, which are stored on the local disk, and with a second interface, it can be sent to the ENAMS server via the internet. So that's only a short calculation of the amount of data we have to store. And as you can see, if we only store the raw data, we get about 140 gigabyte. And this is nearly double as much if we also store the calibrated data, so we can reach 5 years, nearly 5 years of operation without the internet connection, and no data is lost. So now a main important point is the, let me say, analysis of the measurement capability and tolerances, and derive from that the alignment procedure. So we did an investigation of the linearity, frequency response, temperature dependence per system element, but also for the whole system. And we analyzed or established, identified the transfer function. So if you look into the system for alignment, then this, let me say, diagram will help. These are the main parts which have influence on the signal. That's the antenna amplifier, the cable between antenna and receiver, because it has a certain attenuation, then the filters in the receiver itself, but all the other parts like retire or the software has no impact on the frequency response of the system. So, and as the system is measuring the logarithm, I put it in here. That's the logarithm of the transfer function which we measure. And here in the upper left diagram, first you see the attenuation of the cable. So I took the main data points from the data sheet of the cable, but Klaus measured it also in his lab at lower frequencies to have a better fit of this numerical function. So, and this is the green curve, because we need this function because in each spectrum we have about 100,000 data points, and it's easier for the, let me say, calibration for the alignment to have a numerical function that gives you the attenuation at each frequency point. So the same holds for the filter curves of the low pass and high pass filter. We also fitted them with an analytical function. And how is this done? So Jörg Logemann provided a device, a so-called pulse chain generator. So this is a small circuitry which generates very, very short and sharp pulses, and all the harmonics form this kind of spectrum. So this is a peak every, this is a peak every 100 kilohertz. So, and I fitted the envelope here. This is the lower left diagram, and the reference curve for the further calibration is this orange curve. So if you feed the signal without attenuation in our receiver, then you get this diagram. But after the alignment, you have this spectrum here. And if you look to the Y scale, we have a deviation of, let me say, worst case, plus to minus 0.2 dB. So if we would do 100 measurements in a row and take the average, I think then the result would even be better. So, and in future, we will also include the frequency response of the active antenna. And Klaus Logemann provided us with some data value pairs here, about 50, which are, let me say, representing the K-factor curve of the ENAMS 2 antenna. So, and I tried to fit it also again with a numerical function, which is the orange curve here. And the red line shows the difference of the orange curve of the analytical function to the data points. So if you look on the right-hand axis, on the axis of the right-hand side, you see the deviation, which is better than 0.005 dB. So if the data is calibrated, we can then generate the spectra, which is shown here in this diagram. This diagram shows the automated data pipeline we use for ENAMS. you have the measurement here, and the measurements of 1 hour, 6 measurements are put in a small database file, which is then transferred to the main server in the so-called input table, database table. Then we check the data, if the data is plausible and complete. And if this is the case, the data is taken over to the main DB here. And every hour, when we received all the data from all the stations, we do the noise floor calculation, put the result again in the database, because then evaluation goes faster. And after that, we have calculate the noise floor. We apply so-called feature detectors, and I will explain later what this means. So the result of the feature detectors are also put in the database, and at midnight we are able to calculate the standard and generate the standard diagrams in HTML and PNG format, which are then uploaded to the web server and can be watched at and looked at the next day. In the team, Klaus and me, we have also software available that we can generate individual diagrams, which allow a deeper analysis of the data. This is an overview. I will not go into the details. This is an overview of all the diagrams we are providing at the moment. Spectrum plots, power density plots, field strength diagram. Then we have the noise curves, a single curve, multiple curves per day. We have the heat map. We have also time series, which is currently not published on our server. We can do some statistical evaluations, and there are also some diagrams for the diagnostic of the system. Now we come to the calculation of the noise floor. We were visiting the ITU colleagues in the Netherlands 3 weeks ago, and there was an interesting discussion on the noise floor. So one thing is to measure the spectrum, the amplitudes, the signals correctly, but it's also of interest, especially for the ITU, which wants to use also our data, that we calculate and derive the noise floor correctly. And there's an ITU procedure which describes how to do it. And in the discussion with the colleagues in the Netherlands, we came to the result that our procedure is not exactly the same, but it's very close to the ITU procedure, and which is shown here in this diagram. You see a typical spectrum. You see the minimum. That's the red line, and if we apply our procedure, that's 20% quantile. This is represented by this orange curve, and this orange line follows pretty well the bottom line here of the noise of the spectrum. So, and also to see if our measurement system is showing the right variance, I did a simulation. On the right-hand side, you see a measured spectrum here with our 20% quantile. So it's about 2.2 dB below the average here. And on the right-hand side, I did a simulation with similar parameters. And as you can see, the variance of the signal in both cases is in very good agreement. So this I will skip because ITU provided also, let me say, a procedure where we can check if a channel, a frequency is carrier free. This is a very, let me say, complicated mathematical procedure. You have to calculate some values, some so-called eigenvalues of a matrix, which needs a lot of computational effort, and shows if a channel is carrier free or not. So more interesting is the future of ENAMS. So we did some investigation for the future developments, and the first question was could we do also some measurements in other frequency ranges? So could we extend the frequency range? So I did the first, let me say, investigations with different kinds of SDR. So with the RSP1, for example, because this is a relatively, let me say, good and cheap device, SDR receiver, so I checked it, but the software library you get with this device is so limited that it's good for SDR applications where you use it as a receiver, but not very well suited for measurements. So I dropped it. So the next candidate we are investing is the RX888. That's an open source project. It contains a 16-bit fast ADC with about 130 megasamples per second. Looks very interesting, and this is currently what we have under investigation. So that's the first kind of extension. The second is the signal analysis, because we collect more than 10,000 measurements per day, so it's impossible to look through the data by hand. So therefore, an automated screening of the data would be desirable. So, and I think we will do it in 2 steps. First, I introduce so-called feature detectors, and in the next 2 slides or 3 slides, you will see what it means. And this is the preparation then for the application of AI, because we need for the AI some training data, which I want to get with the feature detectors. So what is a feature detector? So again, I have shown you the VDSL spectrum, which you can see in the upper left here. And these, let me say, signals here between 3.8 and 5 megahertz and 8 and 12 megahertz clearly are linked to the upload sections in the VDSL spectrum. And so if we look a little bit deeper in the band plan, then we learn that in these sections we have subcarriers, and the subcarriers are spaced every 4.3125 kilohertz. So in uplink section 1 we have about 330 carriers, and in the uplink section 2 we have about 800 carriers. So if we now have a closer look to the spectrum here, in the inset you can see the range between 3.8 and 5 megahertz. And if we look here, zoom in, then we see, besides the carriers here, we see the small wiggles here, which represent the subcarriers. So what did I do? I made an amplitude filter to get rid of these carriers and looked only into the remaining part and did the FFT of the remaining spectrum, and the result can be shown here. If you do the FFT from the filtered spectrum, then you can clearly identify the peak at 4.31.5 kilohertz, which corresponds to the frequency of the subcarriers, to the spacing of the subcarrier. So we can also measure the amplitude, and this is then put in the database, and we could do some statistics over all measurements for VDSL. So a second detector is what I call weak periodic signal detector. So if you look at the spectrum, you see here regions in the spectrum with different kinds of harmonics. So with a very low or small spacing here with a larger spacing. Again, I did a FFT of the spectrum, and I got this spectrum down here. But because you see, let me say, the harmonics only in different sections, it's better to apply a spectrogram, a so-called spectrogram, which on the X scale shows the overall frequency, and on the y-axis it shows the periodicity or the spacing of the carriers. So, and if we look at this region here, red marked region, which corresponds to this peak, it shows up in the spectrogram here at 75 kilohertz. And if you go to the next one here, it's not so clearly seen here. It's about 200 kilohertz. It's at higher frequency. So if you go further, you can see it, this area here, which corresponds to this peak in the spectrum, FFT spectrum. And this peak here shows this one. Sometimes the intensity in the spectrogram is very low because, let's say, if the spacing gets larger, the energy density is very low. So it's difficult to identify in the spectrum. I think it's necessary, therefore, to apply AI also to get this information out of the spectrograms. So with this slide, I come to the summary. So I think ENAMS has proven to be a useful tool and supports with its data the protection of ham radio frequencies and beyond. And what can we see as results, especially below 10 megahertz, there is a significant increase due to electronic devices. So, and all the results are compared to the data which are given in the ITU P372. Above 10 megahertz, the noise figures in the ham radio bands are still close to the ITU values in some areas. And in some areas above 10 megahertz, the radio bands are clearly visible as notches in the spectra, and also in some city locations, the noise level is even on residential level. So, for example, in Munich. So we have identified different types of interferers like VDSL and PLC. This we call regulated interferers because they follow the rules and spare out the ham radio bands. And then we have all the non-regulated interferers like photovoltaic equipment, especially the balcony solar power stations, which is now, let me say, trend in Germany. We have installed nearly 1 million of these devices, and they will increase the noise level significantly in the next years. So then LED lamps and other type of inverters, and I think the list will be continued if we apply more and more or deploy more and more devices. So, and also ENAMS can make radio wave propagation effects visible, like the Mögel-Dellinger effect and other things. Oh, that's the end of my presentation, and I thank for your attention and patience. So if you have questions, the time is now. Thank you very much.